shorthand. And this is a time reversal symmetry that will tell us a lot of things, but as you will see, even in equilibrium, it won't tell us everything. In any case, let me show you that this is something you do when you, of course, people don't call this time reversal, they usually call it detail balance, but the important point to realize is that there is always, in this kind of problem, that can be associated with equilibrium, some time reversal. Often there are many, and not a single one. And for every one of those, you get different consequences. And I'm not going to do it here, but there are the fluctuation theorems, for example, Jaroszewski inequality and so on, that are all based on this time reversal property. And depending on which one you use, you can get slightly different formulations of the same theorems. So the important thing to realize is that although detail balance was first discussed as a constraint that I will do now so that simulations give you the right result, this is the origin of this discussion. In fact, it is a much more fundamental thing, and it has to do with time reversal. So what you do when you do simulations is you sum over B of this. So you say that, so this is a sum over B. If you're summing over all the targets, this gives you 1, because the probability that I go anywhere, adding over all the possibilities, gives you 1. So this is equal to e to the minus beta VA on one hand. But on the other hand, it is the sum of P of B going to A and when you look at this, what does this tell you? This tells you that if you started in equilibrium, then you evolve to A, you land in equilibrium. In other words, it says that the stationary measure is proportional to e to the minus beta v of the configuration. So already, and in a completely abstract way, without saying much, the fact that you have a time reversal symmetry tells you, and this is completely general, something about the stationary measure. Okay, so this is one thing. And conversely, and this is a bit more abstract, if you happen to know the stationary measure, then you can express things with a time reversal symmetry, but this is never the case. I mean, you never know the stationary measure out of equilibrium. No, here this. Oh, you start. Think of this as the initial configuration, with the probability of the configuration B, proportional to, propagate it to A, and this is telling you that you get this, which is telling you. Okay, what about two-time quantities? Is everything encoded in this symmetry? Is equilibrium enough to know two-time quantities? For example, two-time quantities, you need to see the response of a system. I kick it now and I look how it behaves a minute later. Or transport coefficients, currents. All these are things that involve two-time quantities. So, for example, viscosity. Now, let me give you an example. It's nice because it's something you will never forget. So, if I have particles which have a certain potential between them and they are in an actual bath, you realize if the bath is made of water in equilibrium at temperature T, or if it's made of honey in equilibrium at temperature T, both are perfectly legitimate bath, and both will, if V is the potential between particles, will lead to the Gibbs measure. But of course, you see that the actual dynamics of the particles in honey is not the same as the one in water. And if you looked at the time it takes, for example, to crystallize, to give an example, or the viscosity of a system of particles under the effect of a thermal bath of honey, it clearly is not the same as that of water. So you realize that even if you are, these are two perfectly legitimate thermal baths that lead to equilibrium, don't expect that, for example, transport coefficients, thermal conductivity, electrical conductivity, viscosity, and two-time quantities in general, it's not enough knowing the Gibbs measure or the microcanonical measure. For that, you need to solve the dynamics. So equilibrium is quite a miracle. It allows for things, it forbids other things, and it gives you everything without doing dynamics. It makes you sidetrack completely dynamics for one-time quantities, but not for two-time quantities and things like that, where you really have to solve the dynamics of the problem. So in fact, when you're calculating equilibrium, when you're calculating transport coefficients, you really are not in a much better position in and out of equilibrium. But still, you can use a lot of things. So that's one thing. The other thing I would like to, and now I'm going to go on to do what constraints does equilibrium pose on two-time quantities. As I say, it doesn't fix them completely, but it gives some constraints. One thing, as I said, that you lose, so one thing that you have thanks to equilibrium is that for one-time quantities, you have Gibbs or microcanonical or something like that, so you can do a completely static calculation without making any allusion to dynamics. Another thing is that, remember the ratchet, just detail balance tells you, just by looking at two subsequent points with the same energy, that there cannot be a current that goes that way. And then you ask yourself, what happens when I break detail balance? Will there be a current or will there not be a current? And this is, I think, one example, and there are so many in active matter, which I would call the why not questions. So the why not, a lot of the questions that arise when you do active matter or non-equilibrium matter are of this nature. You ask a question which in equilibrium the answer is no, this cannot be this way because equilibrium doesn't allow you because of a law like this. And then out of equilibrium you ask, is this going to happen? And the answer is why not? And if not, then explain why. Okay. So I'm going to insist a lot on this because I think it's quite important. Okay, so if I have an observable and I want to know what it is, its average at time t, clearly I do this is the job precisely of P, to tell you what are the average. I can do two-time averages, so typically denoted like this. Averages, of course, are averages over the noise, over the distribution, and ultimately averages over the oscillators I kicked out of the game a while yesterday. So this, in the notation of yesterday, what did I do? So, which means, in other words, that this is propagating. This, if this starts in x prime, this is the probability of going from x prime at time 0 to x at time t. This would be the probability of going from x at time t to, at time t prime, 0 t prime, 0 t prime at time t prime to x something at time t, and this would be the integrate of the final time. So this is what and this would denote CBA. Concretely, what this means is that I start my process at time 0, make my Langevin process, record the value of A at time t prime, continue the process, record the value of B at time t, make the product, put it on a table, stop, restart the experiment, start it again at t equals 0, and of course the random number sequence will be different, so it will move in another trajectory. Again, I record these values, I make the product, put it on my, and keep on iterating until I get a value that stabilizes. So what happens with this correlation? So when t prime, the smaller time, goes to infinity, you would expect that the system goes to equilibrium, and we showed yesterday that it does, and we showed a minute ago that it does. So if it goes to equilibrium, or if it goes somewhere in any case, CBA will go to t, will be a function of the time difference only, which is very natural. You prepare a glass of water in bizarre conditions, the water is moving and it has temperature gradients, whatever. Keep it there for a while, and then if you wait for a day and make 2 subsequent measures at 2 different times, or if you wait for a month, assuming it doesn't evaporate, and you make two measurements, it cannot depend on which initial time, and it only depends on the time difference. This is what is called stationarity. Equilibrium implies stationarity, but stationarity doesn't imply equilibrium. For example, when you have a bar with 2 temperatures and heat is flowing, the situation is stationary, but it's a non-equilibrium situation. We will talk about that. When could this fail? Well, one obvious reason for it to fail would be that V is like this. In an unstable problem, it just runs away. And of course, you cannot expect anything to reach anything stable. Such things happen. For example, growth of surfaces, it doesn't reach as far as the height of the surface, doesn't reach a stationary situation, it just runs away. So you cannot expect to have a P of H, let's say. You can have something related, but not a P of H. Another more famous, or maybe physically more relevant, is when V is extremely complicated, and then it may take extremely long for the system to find its happiness in equilibrium here. This is the case of glasses, most famously. I'm going to go through a bit in more detail which cases take very, very long to equilibrate. Another very famous example of a system that takes long to equilibrate, fortunately, is the solar system, which is very much out of equilibrium, because in equilibrium it will be something either collapsed or things ejected. And it keeps being in a metastable state for reasons that I'm going to tell you in a while. Okay, so these exceptions will make your system either take very long or never become stationary. But otherwise, in normal systems, water or a crystal, etc., these things don't happen. But half of the things we have around us are of this kind. Even innocent metals have all sorts of defects that take very, very long to anneal spontaneously, and so you are in a situation where you're stuck in some metastable state. Okay, so now stationarity, or also known as time translational invariance, because if you add a month to t prime and to t, you get the same difference and you get the same value. So other than that, there is another quantity that is important, which is the response. So the response is the following. You have a potential V, which is time independent, and then you give it a kick in some direction. So some observable, you give it a kick, let's say at time t prime. A kick means an impulse whose very narrow and whose area is 1. And what you ask is, how does another observable B at time t depend in the presence of the kick in the limit when the kick is very, very weak? So this is the time at which you observe the thing. This is the time at which you kicked it. And I'm going to do BA because I observe B and kick at A. So this is also, well, it will be in a second a two-point function. So now linear response says that giving it a kick at 3 hours ago plus another kick an hour ago plus a different kick an hour and a half ago, you can obtain the total result. Linear response means by addition of the effects of all those kicks. Of course, it is an assumption, and it's only true if the kicks are not very strong. But if it is true, it says that the expectation value when h is instead something like this, so this is time t, is simply the result of wherever you started so this is linear response. And again, you would expect that if I have a glass of water which I prepared and is equilibrated, and I give it a kick now and I look 1 second later what happened to something, energy or whatever, and if I do the same thing tomorrow, the result will be the same. So provided I also look 1 second later. So also this, by stationarity, in equilibrium or at a stationary state, this will be something that becomes translationally invariant. Okay, up to here, this is what equilibrium gives me. Now, equilibrium also gives me, and now I'm going to prove it, a relation that tells me that the response and the correlation are not independent when I'm in equilibrium. These two things are related when I'm in equilibrium. It is something that helps you because then you have to calculate only one thing, but rather than two. But more importantly, what we are going to see is that this is basically the original idea of Einstein, who said, if I put a particle in a liquid, it starts having Brownian motion. So it starts having, on average, a certain energy. So because it is in equilibrium, its energy is given by the properties of the temperature, essentially. Its kinetic energy has to be what it has to be for something that is in equilibrium. Okay, very well. So how does a particle get energy from the liquid? Well, by the collisions that make it dance. But this, of course, is a process that is counterbalanced by the fact that the particle is moving in a viscous medium. So there has to be a trade-off that if the particle is moving too fast, viscosity will slow it down, and if it's moving too slowly, the kicks will heat it up. So this balance between viscosity and noise is precisely, you will see now, the balance between correlation and response, and is the reason why, for the particle, in its talking back and forth to the system, makes the particle have the right energy. It also tells you that viscosity and noise cannot be independent things, because otherwise they would heat up too much or too little a particle that is dancing in the liquid. Okay, this was essentially Einstein's idea, and then this theorem is just a generalization of that. Okay, so now let us imagine that to prove the relation between these two things, we're going to do a process like this. From minus infinity up to time t prime, we are going to apply a small field of amplitude, constant amplitude h0, and at t prime we will turn it off. Okay, so that the okay, so on one hand, with this process, b of t is going to be the integral between minus infinity and the time t prime, because that's the time where it was on, of r of t prime. Let's put minus, we will assume already we are in equilibrium, dt prime, and here h0. It's just a particular case of this thing here. Sorry? I did something wrong. Now it's better? Good. It's a dummy variable. So this is the experiment, and the result is the response function. Okay. On the other hand, because I started in minus infinity, and I'm saying that the system is in equilibrium, whatever I do to it, or at least without and with a little field, the Gibbs measure is going to be this is just the normalization. But now we're saying that h0 is small. So this is p of x at time t prime. We are assuming that it is equilibrium. And so now I develop this in powers of h0. When I develop the top, so this gives e to the minus beta v divided by z without the h. And now I have to develop this and develop this, because this has a little variation because it's the integral of that. When you do this, it's easy. It gives you this. Sorry. This one is very easy. It's just that this comes down. The 1, of course, is the first term in the exponential. And then if you want, this continues. And here I forgot an h0. This is order h0 squared, which we will neglect from here onwards. This terms comes from differentiating the log of that. I'm sorry, here, just to make no hypothesis, I have to say that potentially if B has an expectation value, so this is the excess with respect to what is the expectation value, if there is one. Normally you just don't use one, but I will do it for just to make it nice. Okay, so this is just the variation. So now what do? Well, now you know what the expectation of B is. I have it here. Only that I will have to plug in the evolution acting on this. So this is going to be B. So B of t is going to be B of t0, of t, sorry, plus, and then we need the first term. So, sorry, I will do it slowly. So the expectation of b at time t is the integral of b times I propagate from t to t prime h, and here I'm going to put the initial distribution, which by assumption is this one here. And this corresponds to calculating the process here in a different way. So if now I have to plug this into this, and this is in the presence of H0. Okay, good. So now I have to plug this in here. So the first term, as you see, it's just replacing this by the initial distribution with H0 equals 0. So this is simply exactly the same thing as this one. And this corresponds to this term, which corresponds to this term. And now we have to add the next term. And now the first term, now the interesting term here is that there's going to be an A here coming from here and a B coming from here. So this first term will give me the correlation of B of t with A of t prime. With this one. This is a constant because we are in a stationary situation, and when I plug this in here, it's just a constant that goes out and it's an expectation of B. So this is going to give me B times A. So when you compare this one with this one, look at it intensely, and you will find that this gives let's put it this way. This is already the fluctuation dissipation theorem in its integrated form, but it's more usual to present it in taking the derivative with respect to t prime, and this gives and this is called the fluctuation dissipation theorem. Sorry? Yeah, but I did it with respect to tau, which is the time difference. Yes. Yes, if I did do it with respect to smaller time, it doesn't have the minus. So So what we learn from here, from this, is that although equilibrium is not enough to know what the correlation is, the correlation, remember, think of honey and water. If the system has a bath that is made of water, the times in your correlation cannot be the same that are involved if it's in a bath with honey. But still, the response to a kick and the spontaneous correlation are going to have the same relation. Okay. Of course, often you see this relation written in Fourier. So this is going to be R of omega, and this is going to be omega times. It is negative if you're differentiating with respect to the largest time or to the time difference, and positive if you're differentiating with respect to t prime. Because when you differentiate with respect to t prime, it's minus the differentiating. But remember, a quick way to remember is that the response is positive usually, although not necessarily, but usually positive, and the correlation goes down, so they have to have a minus sign. Okay, so this theorem as it stands seems like a curiosity or something that makes your life easier if you need to calculate things. But what I want to show you now is a bit variant of the idea, the original idea for Brownian motion of Einstein. And it's nice because it will take us to something that appears also in the literature of active matter. We will do the equilibrium thing, and then we will ask a why not question and have it in what happens for activated matter. So let me consider the following. I have some observable, which I'm going to call Q, alpha, of a system, and I want to couple this. Actually, I have a probe, a thermometer, which is a system simply that has variables Q probe and a Hamiltonian H probe. A nice thing to use is a harmonic oscillator, for example. This is going to be my system, for example, a harmonic oscillator, which I am going to put into contact with here and see how much energy it gets. And the trick of a thermometer is that when you couple a thing like this, you look at this and not that, and because you know your system, you look at the energy it has, and this is the reading of temperature you're making, for example, okay? Or of any other quantity, but temperature is an example, no? So yeah, I have my oscillator, couple it to something, I look at, on average, how much it has of energy, and I say, okay, it is reading that value with a scale. But to make the example nicer, both for the calculation and also as a thought experiment, it's nicer because you can do instantaneous measuring and so on. And let us consider that it is weakly coupled to many copies of the system, always to the same observable, which is Q1, Q2, Q alpha, up to M. M is a large number, and it is coupled weakly. I will couple it as 1 over square root of M. I'll tell you why in a second. So this is a thought experiment. Instead of, to make calculations simple, and it's without much change conceptually, I imagine that I have copies of my system doing exactly the same experiment, but of course with different random numbers. And at a given time, I connect my system weakly to all of these. Okay, so what, let me say that the total Hamiltonian is a sum of all equal Hamiltonians in form of each one of these systems, which is a system I'm interested in, plus h of the probe, which could be, for example, a harmonic oscillator, which depend on Q probe, P probe. And the coupling, I'm going to make it, because it's random numbers, or I expect these variables to be noisy, I'm going to, for simplicity, assume that the average values of Q are 0. It doesn't change much, but it makes life easier. And the coupling, I'm going to make it linear. And why do I do m to the minus 1/2? Because I expect that the Q alphas are noisy around 0, they fluctuate, and when I sum m things that are random, the natural thing is to rescale it by m to the 1/2. So each probe will move like each alpha All right, so now notice that what is nice about having used many systems in parallel is that the effect that the probe has on each one of the systems is very small. So I can use linear response here, what we just did, and here too. Well, here it won't be so necessary. So, so I want to compute h of t, which is this thing here, which is a kind of perturbation coming from the system on my probe. So this contains two parts. One is the random part. So this contains two parts. One is the random fluctuation, so spontaneous fluctuations of alpha. These are random numbers, so m to the minus 1/2 seems like a good normalization. But this system has been bothered by the probe a little bit, and I cannot neglect that. So I need to assume that there is a delta of Q due to the effect of the probe, induced by the probe. So delta Q alpha. Indices are supra or sub for typographical convenience, okay, opportunistically. Okay, but now this thing is the effect on my copies of the system of the probe, and it's easy because this thing here is a field. This depends on t, and I can see it from the point of view of my system alpha as a small field that is acting. So the induced part is very simple. It is just a linear response. A linear response means that it has to have the m to the 1 minus 1/2, and this is the field that is acting, so this has to be integral of r of the system, on my system, of t minus t prime, and the intensity of the field, which is q probe of t prime dt. This is the effect that the system had on this. Yes, R alpha, but remember that the system, which is a copy of systems, R being an average that doesn't depend on the realization, R alpha, I call it R system. And the same will happen with the correlation. Exactly, so the sum will give me, so yeah, and when I do both things, the total result with this one and with the sum of alpha will be 1. So the total effect of this is that at the end of the day, this is the sum, the total value, the complete sum gives me simply something of order 1. It's quantities that are small, but that they are deterministic. And the other part, the spontaneous fluctuations, these there are m terms which are each one is very weak, and so yeah. So, and on the other hand, this term here, the spontaneous one, it's a noise. So let me call it psi of t. And it's a random thing because I said that these had no expectation. It's a sum of a lot of independent random things. I don't know if they're Gaussian, each one of them, but the square of m of those added, it's going to be Gaussian. So, and the only thing I need to know is then that the average is 0 and that the correlation well, it's a correlation between each one of these alphas. Different alphas are uncorrelated. They don't talk to this order. They don't talk to each other. But the correlation of Q alpha with Q alpha is the correlation of the system, which I call C alpha or C. So C alpha equals C system of T minus T prime for all T prime. So at the end of the day, when you do the sum, this gives you C of T minus T prime of the system. So big equation. And integrating once by parts. This is the same. Now I'm going to use the fact. Okay, so I will make 2 minutes of silence so that you contemplate this equation. Yes. Thank you. Um, and now here comes the, yeah? Uh, no, 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 it goes away because when I multiply 2m to the minus 1/2 to get the correlation of each alpha, that gives me a 1 over m. And then I add m of them, and this is the reason why I rescale them with 1 to the m to the 1 minus 1/2. Now remember that, and okay, so now up to here, nothing, but now let me use the fact that the R of the system, we assume the system is in equilibrium, is minus beta dc of the system dt, or t prime if you want, with a plus, okay, as advertised before. Yep. Which one? Yeah. No, the response was defined with a minus sign. When we define the response to, if this is what you ask me, if you define the response to something, you define it already with the thing having the minus sign, because it corresponds to something that has been added. You see, the energy itself has a minus sign. So I think that this is. Oh, yeah. So I shouldn't have. Yeah. So am I? You say that ht should be the minus of this? I'm not sure. No. It's all right. Okay, there will be an additional in a second, yes. So let here. Sorry, I'm on my feet like this. Okay, so up to some doubts about the minus sign, look at this. Now, up to here, I didn't say that the system was in equilibrium. It could have been anything, because I only used linear response. So the relation between these two things is still not known. The moment I say that they are in equilibrium, on the one hand, I know this. On the other hand, I can integrate by parts this, and this is going to give, this is the derivative. So now I can put C system with a beta here of t minus t prime, and I have to differentiate this one. This is integration by parts, and maybe here I'm making a mistake with a and there is a boundary term which I am not going to say much. It is exactly the same situation that happened with a counter term. I'm not going to say much about it. It's the same. Okay, up to one dubious sign. If now I call beta c, I define it as gamma. No. C. Yeah. So this is an integral over all the past, so I can put one single prime and it's okay. And here I can do the same thing. So using a, yes, and here. Sorry? Oh, and that is also true, yes. Okay, so now, okay, now we're all right. But I can put a double prime even if there is no single prime. I mean, this is not illegal. Yes. I don't. Oh, another dt. Yeah. Okay. Good. Good. Thank you for your attention. So If you now decide to call gamma C, call it gamma, you see that up to this term, which doesn't change the argument, it just modifies the energy, and it's a counter term we discussed. This is telling me that the probe is feeling my system as a perfectly legitimate thermal bath, because the probe is undergoing a generalized Langevin dynamics, exactly like the one we wrote the other day. No, the counter term, I would need it in the sense that the probe is acting not on its original Hamiltonian, but on the Hamiltonian plus a quadratic term. I don't care very much about this, but if you care, you would need to talk about a counter term. It's exactly the same situation as before. So let us pause 1 second to see what we have done. You see that I have more or less morally repeated Swanzig's calculation of yesterday, but instead of integrating away our harmonic oscillators, I have used linear response for a system that can be very general. Notice what happened here. There are two effects. The effect of the spontaneous fluctuations, which I treated in one way, of my system, and the effect of the induced by the probe. When you say that the probe does something on the system and the system back reacts, which is what we are doing, the effect is much smaller, but at the same time it's non-random. So that is why the m to the 1/2 became 1 over m in one case and 1 over m to the 1/2 in the other, but one of the terms was random and the other one was not. The induced term was not. So, but it gives you the physical interpretation of what the response is doing. The response is telling you, the response of the system, what a probe is doing on the system comes back to the probe by an effect that I do something on it and it comes back. But that's exactly what friction is about. As you move, you do something to the table and the table stops you. So this is exactly the argument that Einstein had in mind with the Brownian motion. This would be playing the role of the fluctuations of the molecules that are hitting against you randomly, and this is the effect of your molecule moving, drifting on the fluid, producing something on the fluid, and this comes back to me. And this coming back that has to do with how I'm moving is precisely the viscosity. And it's telling you that these two terms, which are these two terms, this is the fluctuation, this is the dissipation, have to have a balance because I want my probe to have a balance, to have a given energy. Now imagine it's a harmonic oscillator and I'm just measuring the energy of the harmonic oscillator as a way of using this harmonic oscillator as a thermometer. It's the balance between these two guys, also known as temperature, here, that is telling me how much energy on average the probe will have. So fluctuation dissipation is a way of saying it's not just a thing that by chance makes two quantities be the same, but it's also something very important that it's telling you how exchanges are made between parts. Okay. Is this, I think. Okay, yes. No. Sorry, thank you. Sorry, the confusion comes from having used system and probe in an older version. Okay, another important thing, and this is going to, I hope, be related to something that I hope Yariv Kafri maybe talks, is the fact that notice that Q doesn't, I didn't say anything about Q, because the fluctuation theorem that I use for Q, the fluctuation dissipation theorem, is valid for this relation, not the actual correlation or response, is valid for any variable, which means that had I coupled my probe to some other m all equal, but m variables of the system, I would have measured exactly the same temperature. Because the fluctuation dissipation, which is a relation between two things, it doesn't matter what the things are, it is the proportionality that counts. So this means that an oscillator or anything used as a probe will measure the same temperature wherever I plug it in my system, to whichever variable of the system I couple it. And that's very important because you will see that in active matter this doesn't happen. And in general, in out-of-equilibrium systems, there's no reason why this should happen. Another thing is that the probe itself doesn't matter very much, because the probe, whatever it is, whatever its Hamiltonian is, the important thing is that it is undergoing a generalized Langevin process, so it will be in its own equilibrium. That's the only thing I need. Okay. Okay, now quickly. One thing, now we're going to list a few ways of kicking the system out of equilibrium. All of them are interesting, and all of them have been applied and are intensely studied. Okay, so let me make a list. So, one, let us so you establish, this is your system. You establish a current moving through the system. Very old, the Fourier problem. And this produces a non-equilibrium steady state. And this is how these situations are called. So you have something that doesn't depend on time, or depends only on time differences, but still it is non-equilibrium. Of course, I can define correlations and response for the parts of this system, but they're not going to satisfy fluctuation dissipation. At least not exactly. Another one that I hope Ludovic Berthier probably will do is, or will use, this is one variant. So you couple the system to two baths which have different temperatures and have different memory kernels. If they have exactly the same memory kernel, then it's trivial because these two lump into the same thing and you don't get anything interesting. Just the sum of two Langevin equations. So why is this interesting for active matter? Because it is a bit like this. But here, every single particle is subject at the same time to two baths. One is the violet bath with temperature T1, and the other one is the orange bath with temperature T2. And in my case, this one corresponds to fast variables, and this one operates on a slower scale. So it mimics a bit what active elements do. They are kicked in the fast scales and disperse their energies in the low ones, or you could do, of course, the contrary. Because the time reversal symmetry has in it a temperature. Which one do I put? There are two. If the temperatures would be the same, then no problem. In fact, okay, I will say that later. I don't know, I don't think anybody knows how to what stationary configuration this takes you. It takes you to something, but there is, as far as I know, no general expression for what this takes you to. It just pumps energy on one scale, takes it out on a different one, and you don't know what to do. What we did years ago, and it's relevant for glasses, and it might in some occasion be relevant for active matter, I don't know, is to study the case in which one thing is very, very much faster than the other. So there is one bath that acts on the very, very low, slow scales, and another one that acts on the very fast scales. Then you can solve the problem, and it gives you a kind of generalization of the Gibbs measure. But only then. Okay. Ludovic Berthier probably is going to describe what happens when you do this to a glass. So it's an activated glass, activated because you're pumping energy on one scale and retrieving it on another one. Okay, another popular way to drive a system out of equilibrium, which now goes under the name Floquet, especially in quantum, and you have to use that one because that's a fashionable name, is this one. So you have time-independent Hamiltonians, but you drive it periodically. And then this one doesn't take you to a non-equilibrium steady state, but it takes you to a periodic state, which plays the same role of time translational invariance. In a way, it's a generalized version. Once you are in this world, you don't know how to solve. When the frequency is very high, you can imagine that you can do an expansion and do some sort of averaging over V2. But otherwise, outside those limits, there's nothing particularly powerful you can do. You just have to solve the dynamics. Tomorrow, the day after, what I'm going to do is solve completely a problem of this kind to show you how non-equilibrium happens. What I'm going to use is a macroscopic system. So, as I said, just to show you the two aspects, the system is going to be, on the one hand, macroscopic, which will make it solvable, but it's going to be non-equilibrium, and we'll see all the things we lose on the way. This is now very fashionable in the world of quantum systems, and you get a phenomenology that is interesting. It was also treated in the world of ratchets. So you have V is this, or directly, V is this. So you flash your ratchet like this, and this could be something else. And again, when you flash a ratchet, then the system moves in one direction or in the other, and you no longer have this thing of not drifting. Another kind of non-equilibrium, which is different because now it is not steady state and it's not even periodic state, is what happens, as I mentioned before, what happens when you evolve a glass, a system that has very slow dynamics, and you start with a configuration. The system has a dynamic that never reaches the place it wants to reach. So if you want an example of this that is very simple, is when you have two phases that are in competition. For example, in a ferromagnet, it could be up and down spins, or it could be a mixture of vinegar and oil, and the drops of oil want to be only one drop of oil. This is the preferred state, and the vinegar just another big sea of vinegar. But this takes time. They have to coalesce, and this is a slow dynamics. Well, in actual life, the domains or the drops of oil can take very long, and you can find yourself in a situation where your system, such as you have it, is still growing and will continue to grow. Typically, the growth laws of these things can be t to the 1/2 if you're lucky, or log of t if you're less lucky, if the system is dirty, for example. And at all the interesting times, you have lots of domains that are there and that have to grow. Another example is a metal that has lots of defects in the crystalline structure. These eventually should go away, but they don't, and they don't in any reasonable time. In fact, metals are strong because of the defects. If they went away and they produced a perfect crystal, the aeroplane wings would just fall off. So, because what makes the aeroplane wings strong is the fact that they have defects that are, so it's an essentially non-equilibrium phenomenon. So this is usually referred to as glassy dynamics or complex landscape. And the point is that you are not breaking equilibrium because you are doing something to the system, simply that the initial condition was far away from the equilibrium, and in any reasonable time you don't manage to equilibrate. So, and you can have a combination of both, an active system which is bothered by forcings that don't derive from a potential and still are also glassy for other reasons. Another example is a system that has, so this would be A, complex landscape, and B would be a system that has almost constants of motion. So for example, the planetary system, the solar system, as you know, it's a series of Kepler problems that are weakly interacting, in the sense that Mercury bothers Venus a little bit, but not too much. So to a first approximation, Mercury, Venus, Earth, and so on are doing their own thing, but they bother a little each other, and in fact this will lead Mercury to be ejected in some 5 billion years or something. It is an unstable system. You can prove that the system is chaotic, and it is drifting very slowly, and it will continue. It's not in an island of stability or anything like that. It is really chaotic, but because these constants, approximate constants of motions of each planet are rather good, this process is very slow. That's one example. Another example is weak turbulence or wave turbulence. So when you have waves like water waves, but that are weakly nonlinear, they interact weakly. So for a long time you can consider them like waves, but then you have to consider that they also dissipate and interact. So that would be another example of a system like that. There is one last example I thought I was going to give in a bit more detail, but I think I'm not. It is the Fermi pasta Coulomb chain, which you probably heard of. It was the first numerical experiment, at least the first famous numerical experiment, where you have beads and they are coupled with some potential which is of the difference. So what was done is they wanted to equilibrate this system, so they started it in some bizarre configuration, and they said, okay, I let it go, and they wanted to test statistical mechanics, so they said, this should equilibrate, why not? And it took them all their powers, the computer powers of the 50s, to not equilibrate it. Of course, today we know that it does equilibrate. We have a bit more power than in the 50s, but still it is an extremely slow process. And the reason, again, is that this system is very, very closely related to a system that has solitons that live forever. It is almost that, but not quite exactly. So it's in the same situation as the solar system. It is almost has constants of motion, but not quite. So these solitons live a lot, but then in the end up by dying, but they die very slowly, just as Mercury will die very slowly, and then the Earth, and then the rest. So this is another famous system. Here, the slowness of dynamics and the slow approach to equilibrium is not due to ruggedness of landscape, but of weakly coupled, almost integratable parts of the system. Yeah. Yes. Yes. Okay. So what? Yeah. Yes. So I guess, but you should know. I'm not sure that that is a problem that can be thought of this way. But imagine that I give it kicks that are not frequent, and that no, I would say the contrary. So I don't know. It depends on the scale for the grains to use their friction to lose their energy, how big it is with respect to the frequency of the kicks. So you would put a very low temperature or zero temperature if you want. That this is zero temperature that mimics the loss of energy due to friction. This will suck in all energy you have. And the kicking, you would put it in another scale, and you could put infinite temperature. So one of the things, you can put it at infinite temperature and the other one at zero temperature. And the trick is that this is not correlated like this. And now, is the granular problem a case where you can consider that you inject in the fast scales? And I'm not very sure. Maybe it's not a good model for granulars. This. Yes. Yes. Sure. Yes, no, sure you need a fifth number. This is only one very simple example of how you can have a bath that is somehow inconsistent from the point of view of equilibrium. But of course you can do many other things. It could not be Gaussian, it could be kicks that are deltas, as you said. Absolutely. Yes, of course, this is just, of course, you surely. But in any case, in the granular matter, even if it's not exactly of this kind, you still have a process that is essentially infinite temperature, which is a kick. A kick is something where you give, but you don't ask anything. And it has another process, which is essentially zero temperature, which is the friction, which accepts everything but doesn't give back anything. But then they are not of this kind, maybe. Yeah, sure. Yeah. Yes, sure. show. I don't expect so much of this, but let's. Okay, sorry, I missed one number 5, other than the number 5 that was proposed, which is the following. This one is more abstract. I have a system, I'm doing a simulation of a liquid, and I say that there are, a liquid when it's very cold, it has regions that move fast and regions that move slow, and then this role of who moves fast and is exchanging all the time. It has blocked regions and less blocked regions. This is typical of something that is beginning to wanting to be a glass. Now imagine that I do the measurement, but I decide, because I wish so, to only measure the regions, measure other quantities, density for example, but of regions that I observe are moving fast. So I am conditioning what I am looking to some criterion that has to do with what's going on there, to some other variables. Then this is not equilibrium, but is not because the system is not in equilibrium, but because I am not taking flat averages. Or another way of saying the same thing is I can say, well, I have this system here which has a magnetization that depends on time, but I am going to only consider the system in an interval in which the average magnetization happens to be m that I chose. So I do the experiment, and this m fluctuates, but whenever it happens that my average corresponds to something that I decided I want to see, then I measure other things. I measure the correlation, the density, whatever of the system. So I am doing an observation conditioned upon something that I impose. This makes contact with the theory of large deviations, and it's another way of being out of equilibrium, which is conceptually different from the others, but still, if I measured correlation and responses, which I could, I just have to repeat the experiment so many times until this happens, but then at those times measure, it would violate fluctuation dissipation, it would violate everything. Yeah. That's a good question. On the linear regime, maybe. Further away, I'm not sure. On the linear regime, but you need time correlations because, well, you know this, because your no, no. And this, as you must recognize, goes back to your question you asked Meran about the boundaries, and if imposing them, it was the same as condition. But of course, Meran was doing an equilibrium calculation, so there clearly it is the same. But if you looked at dynamics, it's less obvious, I think. Okay, so now a quick thing. Just how does a non-equilibrium? One of the things I said is that once you're out of equilibrium, you don't know what the measure is going to be. There have been many attempts to find some modification of the Gibbs measure that would be okay out of equilibrium, and I think it is fair to say that none of them has been very successful. The only perhaps exception is for granular matter, which is out of equilibrium, a proposal by Edwards, which is called the Edwards Ensemble, where you propose that all the configurations that you can imagine that are blocked, that are stable of the granular matter are equiprobable. You don't have any reason to suppose that, but he proposed that, and it more or less works. So there you have something where you have absolutely no principle, but it more or less works. Okay, so this is Edwards, but in general, the ideas of doing flat measure for no reason, because you're out of equilibrium, are associated with Janes. And this also goes by the name of maximum entropy principles. This is proposing that something is flat because you don't know how to do better. Sometimes it works, but when it works, you don't really, you should argue why, but most often it does not. Okay, so now, just to give you an example, one of the few problems where equilibrium was proven for a deterministic system is the so-called Sinai billiard. So you have a billiard like this with hard walls. These are forbidden zones. And your particle moves in here with periodic boundary conditions. So if it exits here, it will enter here. Sinai proved that this system is ergodic, and it has all the properties you would like. In other words, that if you send a particle here with a kinetic energy E, which of course is conserved, you can prove that the probability of being in a little square anyway is proportional to the volume, and that's it. You can really prove that it is explored democratically. It's extremely tough to prove such things. You have to really be good. Well, the velocity is constant in this case because you only reflect. You don't do. Yes, absolutely. On the sphere, yes, absolutely. Okay, but this is really, don't expect that you will be seeing many proofs for many systems. This is really tough. Now, this is an interesting case because you can now take this system and apply to it a force which is constant, but it does not derive from a potential because we have periodic boundary conditions. So something can accelerate forever. It doesn't globally derive from a potential. You cannot write that this is you cannot write this because this, if it has a value here, it should have the same value here. If not, it would be like a ratchet. Okay? So it doesn't globally. Once you apply this, the whole thing just collapses, and you no longer have equilibrium. So you could ask, okay, what does it look like? So imagine that I solve this problem. I'm not going to do it in detail, or maybe next time, if you really want, I can do it a bit. No. So you can, well, I'm going to say it a bit more in detail, maybe next time. You can apply this, but constraining the system to be always at the same kinetic energy. For that, you have to do some work, because you have to do something, because this will accelerate. So x dot is going to be E, and so x is this, and y dot is going to be 0 unless you are crashing against a wall. And then if you have to add something, if you want x dot squared plus y dot squared to be constant. Maybe I do it more in detail next time. You can constrain your system to keep on being in a constant energy. In any case, you can also add friction, and it will do the same thing on average. So you can add friction to your system. I have problems with the primes and the seconds today. Okay. So how does this look like? Well, imagine the forcing is terribly strong, and you then have to put a lot of friction. One thing that I didn't mention, but I forgot to mention about items 1 to 5, is that when you're doing periodic driving, for example, you cannot do that to a system if you don't add a thermal bath. Because if you start periodically driving a system, unless it is a harmonic oscillator, it will heat up. So remember that some out of equilibrium systems, depending on how you define them, need a thermal bath, need some mechanism that will take the heat away. In the case of the double Langevin bath, that's okay, because there is a friction that will do the job. But if there is no friction that does a job, if you take a Hamiltonian system and you make a potential that you will never that oscillates, you will never reach a steady state because you will keep on average pumping it with heat. So you need to add some friction somewhere. If not, the thing is going to just heat up. So remember, this is a point to bear in mind. Forced systems, to be able to become stationary in cases, and it's very obvious which can have to be, the heat has to be taken away. Okay, if the forcing is too large, you can convince yourself that the trajectories that dominates is one that does here, rebounds but quickly loses its velocity because there is friction, which you add here, and does this until it escapes here, and then it does like this, and then it comes back on this side, and the same on the other side. And that's all you have. If something happened to be here, it will go here, here, and rejoin this one. So any other thing anywhere will end up by having, for strong, so you see, for strong driving, this form. So you realize that now about your question, who was it that asked it, about the velocity vector. Yeah, the velocity vector now is not very free. It's pointing a lot of time here. Here, strange thing happens to it because it's bouncing a little bit, and then back again. And the spatial distribution is only very limited. So to answer Julian's question, of your all-energy surface, there are a couple of things, and the rest is never explored. So you see how bad, once you're out of equilibrium, a macrocanonical ensemble can be. Even if you did a thermostat that kept you on that surface, most of it you wouldn't explore. If I have free time, next time I may show to you that, in fact, you can show that once a system is driven, if it's a deterministic system, it will explore a fractal subensemble of the energy surface. So I'll stop here. Thank you.